In this video, we're going to start by looking at the mathematical number e. E is similar to pi in that it is a constant, non-repeating, never-ending decimal. It's approximately 2.718. And if you look at your calculator, you should find at least one E button or sometimes two. So on this calculator, the E buttons are not on the main screen. But if I click on this button that says FUNC, it stands for function, I get more options, and there I see the E buttons. So there's one button that's just E, and if I click on that, it shows me decimal approximation for E. There's another button that says E to the X, and what that does is it automatically opens up an exponent for me to type in. And the reason for that is because a lot of times when we use E, we're using it with a power attached to it, and so it just makes for one less clicking of a button required. So both of those buttons can be used to access E, and you should locate the E button or buttons on your calculator as well. Sometimes they're a little bit hard to find. You might have to access the area where there's more buttons, but you should be able to find an E button or buttons. Now I want to show you this in the book. It kind of talks about where E comes from or what it is. If you look at this, this is on page 667, table 9.1. It shows n, plugging in numbers into this thing, 1 plus 1 over n to the n power. And so what happens is if I plug in numbers, I can see that when I plug in 1, I get 2. When I plug in 2, I get 2.25. But it doesn't just increase, it eventually kind of stabilizes. And so plugging in a million and a billion, even though a million and a billion are very different numbers in size, plugging them in gives you very similar values, 2.71828, and you don't see a difference until after the 5th decimal place. So the idea here is that as n increases, this calculation for 1 plus 1 over n to the n power, that will stabilize at the number e. So that's kind of the idea behind where e comes from. It's in terms of calculus. If you've ever taken calculus, it's a limit, but it's the value that this 1 plus 1 over n to the n approaches as n gets larger and larger and larger. So what we're going to use for E is use it in formulas and problems. It's used in a lot of real life types of applications. And so this one is a function f of x that models the gray wolf population of the Western Great Lakes x years after 1978. And so the question, part A says, according to the model, what was the gray wolf population rounded to the nearest whole number of the Western Great Lakes in 2014? So in this case, what I need to look for to plug in for x is I need to use the fact that the model models the wolf population x years after 1978. So I need to figure out what to plug in for x. X is number of years after 1978. So if I want the population in 2014, what I need to do is subtract 2014 minus 1978. It tells me that 2014 was 36 years after 1978. So 36 is what I plug in for x. So I'm going to plug in 36, 1145, E, 0.0325 times 36. So I'm going to need to use my calculator here. So I need to go back to the main, or I can, probably use my keyboard to type in numbers as well. So I'm going to use the e with the exponent. And then in this one, I don't need to use parentheses. Usually it's best with parentheses. If you're not sure, use parentheses just to be on the safe side. Sometimes if you don't use them when you need to use them, it messes things up. So I'm going to plug in 36, so my exponent is 0.0325 times 36. And so my answer here, I have 3,689.18. Since this is wolves and it says rounded to the nearest whole number, obviously it wouldn't make sense to have 0.2 wolves. Animals only come in whole numbers. So I'm going to round this. This is going to round to 3,689. So that would be my answer that I would type in to MyMathLab if this was a homework problem. 3,689 wolves. So there's a part B to this where it asks you to compare to the graph. Don't worry about that. You can go ahead and do checkpoint problem number 6, which is asking you to use the same model to project the wolf population in 2017. So do this in your notes, check your answer, and then move on with the rest of the video. Next thing that we're going to talk about is compound interest formulas, and we saw this a little bit back in Chapter 8. We're going to see a couple of new formulas today. So first we're going to remind ourselves of what the variables in these formulas stand for. A is the balance after T years. P is the amount invested or the principal. And we have R, which is interest rate. And when we plug in R, we always want to plug in a decimal. So generally it's given to us as a percentage that we need to convert to a decimal. And T is time in years. So we have two formulas we're going to look at here. The first one is going to be for N compoundings per year. And what that means is that when you're compounding, you're basically putting interest that has accumulated on the account, putting that back into the account as principal, and so your interest becomes principal that is then earning more interest later on. So last time we used this formula, we did annual compounding, but you can also use different compounding periods, which we're going to see here. So this formula is A equals P times 1 plus R over N raised to the N times T power. So some possibilities for compounding. You could have compounded annually. Something happens annually, that means it happens one time per year. So that would be N equals 1. The N is the number of times it's compounded per year. So semi-annually means it happens twice a year. So N equals 2. We could have compounded quarterly. Quarterly is 4 times a year, every 3 months, so N equals 4. You could have compounded monthly. So a lot of times if you have a savings account, every month you get a statement where they just say how much interest you earned, and then that interest is put back into the account, so that would be compounded monthly. That means it happens 12 times a year, so N equals 12. Or you could have compounded daily. Once a day means that it happens 365 days a year. Usually we take out leap years just because it makes the calculations a little bit more difficult if we include them, so N equals 365. So those are different compounding periods. If the problem says that something is compounded with a different time period. The other possibility is that we have what's called continuous compounding, which basically means that your interest is constantly being added as soon as it's earned back into the principal. So more often than daily, like more than once per second even, just constantly being converted to principal. So continuous compounding has a slightly different formula. There's no n. The formula uses e. Sometimes it's called the PERT formula. So it's a equals p times e to the r t. And remember, e here is not a variable. We use the e button on the calculator. So we're going to look at example 7. It says you decide to invest $8,000 for 6 years and you have a choice between two accounts. The first pays 7% per year compounded monthly, second pays 6.85% per year compounded continuously. Which is the better investment? So we need to calculate the amount earned in both accounts and then compare them. So we're going to start with the 7% compounded monthly. Plugging in here. Our P is 8,000. 1 plus interest rate 7%. Move the decimal point 2 places or divide by 100. So that's 0.07 as a decimal. Compounded monthly means n equals 12. The n appears in 2 places in this formula. N times t. T is 6. So I'm going to type that into my calculator here. So 8,000, parentheses, 1 plus 0.07 over 12. Now, oops. For my exponent here, I'm going to put that in parentheses, 12 times 6, or I can, do 12 times 6 at 72, and then just type in 72. That would work as well. So the answer that I get here is $12,160.84. So I'm going to write that. Now I'm going to do the 6.85% compounded continuously. Continuously means I use the PERT formula. So 8,000 times E to the, now 6.85, sometimes people have trouble with interest rates when they already have a decimal point in them. You still need to convert that to a decimal by moving the decimal point 2 places. So it's 0.0685 times 6. And then use my calculator again. So I'm using the E button here. 0.0685 times 6. So that gives me $12,066.60. So, which account was the better investment? That would be the first one because I got almost $100 more after 5 years. So 7% monthly is better. So next you should look at checkpoint problem number 7. Do this in your notes, check your answer with the notes that are posted, and then move on to the homework for this section.